Okay, let's get started. And hi, my name is Sean Huang, and my project title is OFDM simulation with cyclic, prefixed, and raised cosine window. And OFDM is just for orthogonal frequency division multiplexing, and it is a scheme of digital communication employed on multiple carriers. The idea of OFDM is to divide high data rate into several lower data rate subcarriers. These subcarriers are orthogonal, so that subcarriers can be close in space, even can be overlapped, without causing intercarrier uh, interference. So in the recent year, the OFDM scheme is become more and more popular because it contains the several advantages. And the first advantage is that it has a high bandwidth efficiency. So in a traditional parallel transmission system, the whole bandwidth is divided into several parts and sent to substreams. These substreams are separated, which makes the bandwidth efficiency very low. However, in the OFDM system, substreams are orthogonal, which means substreams can be overlapped, and that's why OFDM has higher bandwidth efficiency. And the second uh, advantage for them is that it has high resistance to multipath fading effect. And in FDM system, cyclic prefix technique is used. That is copying the values of last samples in OFDM and put them ahead of OFDM symbols. Cyclic prefix is an effect mechanism to deal with multipath fading. It also reduces the complexity of receiver. And the third advantage is it has high resistance to inter-symbol interference. In OFDM system, high data stream is modulated to every subcarrier by serial to parallel conversion and then transmitted, which increases data symbol period. Longer symbol period can reduce inter-symbol interference. However, there are also two main limitations for OFDM, and the first one is that OFDM is sensitive to carrier frequency offset, and the second problem is that high peak to average power ratio. Both of these problems will destroy the orthogonality, which causes interference. So the problem I'm studying is that how the first one is how to eliminate inter-symbol interference and inter-channel interference, and the second problem is how to reduce the possibility of peak to average power ratio. For the first problem, there are two main uh, methods to deal with this problem. The first one is self-cancellation method of OFDM, and this method works in two steps. The first, at the transmitter side, one data symbol is modulated into a group of adjacent subcarriers with a group of weighting coefficients. The weighting coefficients are designed so that the inter-channel interference caused by the channel frequency errors can be minimized. And at the receiver side, by linearly combining the received signals on these subcarriers with proposed coefficients, the residual inter-channel interference contained in the received signals can then be further reduced. So the second method is cyclic prefix. This is the method I picked in my project, and this chart shows how the interference produced. So here there are two carriers, and the the first one is this blue line. The second one is this black line. So since every OFDM symbol contains some non-zero carrier signal, also there's delay signal of this OFDM symbol. In this case, within this FFT interval period. Um, the cycles the cycle difference between these two carriers is not an integral number, which means that when the receive, receiver modulate the first carrier signal, there is interference coming from the second carrier. And similarly, when the receiver receive the signal comes from this second carrier, and there is also some interference coming from the first carrier. So that's a problem. Our solution is that we will insert a cyclic prefix in front of the transmitting signal. So we need to copy samples from this signal and put them in front of the transmitted signal and combine them together as our transmitter package. And for the second problem, there are some approaches. The first one is amplitude clipping, and this method is maybe the simplest method to deal with this PAPR. But the problem is that this method is sometimes is a little, it will cause some distortion. And the second approach is active constellation extension, and this method can improve the power for the transmitted power, and this technique needs to work with a modulation scheme that with a large constellation size. And the last one is window function. This is the method I used in my project. So window function, this is a mathematical function that is zero value outside some chosen interval, and the raised cosine window is one of the window function. I will use this one in my project. So in the performance of existing approaches part, this is my whole simulation architecture. And this is in the receive transmitter side. The first step is to parallel to serial conversion, and then I'll use the QAM modulation, and then go into the IFFT processing, and then insert the cyclic prefix to eliminate the inter-symbol interference and inter-channel interference, and then goes to serial to parallel conversion and transmit the signal through the channel. And in the channel, I also add some noise. So in the receiver side is reverse to the transmitter side. First go to parallel to serial conversion, and then remove cyclic prefix, and then goes to FTT processing, and then use the QAM demodulation to demodulate the received signal, and then goes to serial to parallel processing, and the last we can get the received data. So in conclusion, these two methods can work well, and if I choose a proper blend of the cyclic prefix, the system can eliminate inter-channel interference and inter-symbol interference. And by using the raised cosine window, it is obvious that the possibility of PAPR distribution can be reduced greatly. Okay, so now let's go to MATLAB to see the simulation result. In my project, there are two files, and this one is the QAM modulation file. This one is the 16 QAM demodulation file, and this is the raised cosine window file, and this one is the main function of my project. So okay, let's see the simulation result. Let's see. Oh, okay. Here, the blue frequency spectrum is the spectrum before we adding the raised cosine window, and the red spectrum is after we adding raised cosine window. So we can see that the the magnitude for the red spectrum is much lower than the blue line, and this is the binary streams before modulating, and this is the uh, received received signal. So you can see here there's almost no errors happen. So right now let's reduce the signal to noise ratio. Let's see, go to 4, simulate again. So from here it is easier to see that there are some errors occurring between the transmitted signal and the received signal, and the reason is that, and when the uh, SNR is low and there's a lot of interference, and the delay the delay duration is greater than the length of the cyclic prefix. So which means that, and the OFDM cannot uh, eliminate a lot of errors uh, in this system. So that's pretty much all of my presentation. Thank you so much for watching.